back friends. In this lecture we will prove the Sylow's theorem, first Sylow's theorem. Okay, so in our setup this is clear. Okay, G order of G equal to n, that is p power alpha into m and p power alpha. This is a setup. In last video I explained. Okay, let me write the statement. First Sylow's theorem statement. First Syllow's theorem statement is let G be a finite group and p power alpha divides, then there exists a subgroup of order p power alpha. That means if you give a prime, the maximum power prime divisor, there exists a subgroup. The existence of subgroup is partially true. Lagrange's theorem, inverse Lagrange's theorem, partially true. Let's prove this. We are going to use group action one above level. Let's do that. Collection of all subsets of size p power alpha. So our group is going to inside one of the inside. So but I don't care actually. I will give another way to see. Anyway, our subgroup is going to be here, but I don't care. We are going to see in a different way. I am acting G on this like this. GU such that U belongs to U. I am acting G on this collection like this, and you can check this is a well-defined group action. And what is n? N choose p power alpha. That is the size of this guy, right? And we have seen in the preparation video, p does not divide n. This is going to be a very big part here. Since p does not divide n, whenever we have a group action, we can split that set into G orbits, G acting, G orbit. Okay, so the order of the set equal to summation of G orbits. Perfectly, this is going to be finite because it's contained in power set of G, and power set of G is nothing but 2 power, order is 2 power G. This is finite. I can write like this. Now, since p does not divide order of this thing, order of the collection, there exists at least one U belongs to collection. The orbit of U does not divide by this thing. See, if every orbit divisible by p, that means this is divisible by p. That means, and this is not true, but this is true. Hence, it is not divisible. Hence, there exists at least one orbit. I am choosing that orbit. Okay. Now, let stabilizer of U. Let stabilizer of U, the particular that is inside the G. Okay. And we know by orbit stabilizer theorem, order of G equal to stabilizer of U into orbit of U, and p power alpha divides order of G. LHS is better way to write. LHS, that implies p power alpha should divide RHS, in fact, and p does not divide order of U. That implies p power alpha should divide step of U. From here we can conclude that stabilizer of U greater than or equal to p power alpha. This is the first equation. But stabilizer of U also should divide the U, because we have seen that, right? We have seen in the preparation video. This is what happened in the left regular action, because G acting here and power set of U like this, power set of G like that, GU sorry, in the sense G capital U equal to G U, U belongs to U. So we are restricting that action, we are restricted that action to this thing. This is invariant. Okay, this is clearly invariant, you can check it. So the step of U should divide that order of U, but see, U belongs to this collection, order of U is p power alpha, so the stabilizer of U must be less than or equal to p power alpha. So second thing, so 1 combined with 2, we get step of U equal to order of step of U equal to p power alpha, and this is required H. This H what I required. Okay, fine. This is the proof of the first Sylow's theorem. Okay, anyway, I review, this is a short video, I can review that. First, what we did, we splitted this collection is the key. We have taken this collection and we acted left regularly. Remember that left regular, okay, at least let me prove this is invariant. G acts on power set of U, power set of G, and G acts on this. I wanted to prove this is invariant. Let's say let U belongs to this, and this is invariant because G acts on U. This is another V, right? The cardinality of V is same as cardinality of U. How? Because this is nothing but GU such that U varies over U and G belongs to G. Let's define G to G. P of Gx equal to Gx. We have seen in many videos before in class equation, this is invertible function and this is invertible, and inverse is Pg inverse. Okay, and the exactly same kind of image used here. Remember that V is Pgu image, and the invertibility says that both are same U. So this is invariant. So G takes a element again belongs to here. So this is invariant. Then the collection we acted, and in the preparation video we proved that this is not divisible by P, hence there exists at least one orbit and so on, one by one. This is orbit stabilizer key theorem. As I said, orbit stabilizer is kind of a heart of the group action. Most of the theorem goes to orbit stabilizer theorem and come back exactly like our blood. Okay, thank you. In the next video I will prove the second solution, which is little bit tough.